All right, so this is the video for day 2 for those of you that are learning asynchronously today. So you've got your textbook problems on the top there. Okay, these first couple days they're pretty lengthy assignments because we have all of the stuff to review that you already learned. So what I'll do at the beginning of this, I'll just kind of pause on each of the homework sets of answers. You can pause the video and check them all. And then after I just have the list of answers, I have the worked out answers so you can look at those as well. See if you can figure out where you went wrong. If you still have questions, just post it on the content discussion board and either someone else or myself will help you out with that. So again, I'll pause on each of these just for a couple seconds. You can pause the video and check them. So these are all now the worked out answers. Again, I'll pause on each one for 3 or 4 seconds so you can pause the video if you need to see the worked out answers. So the join code I talked about on Friday, so everyone should have that. There's the link in Friday's assignments that tells you what to do, and there's the PDF under the AP exam folder on Schoology. All right, so this you can just do right in your notebooks. It's just a review of a few topics from last year just to jog your memory. So your definition of a derivative. So a derivative comes from a limit. So imagine that point towards the right. It's got some slope between there and the point on the left. Well, as the point on the right gets closer and closer and closer to the point on the left, that slope's going to change. But the slope, as you get really close, is going to only change by a little bit. And whatever that slope is approaching must be the slope at the single point. So that's our limit definition of a derivative. We have the a way on the left and the h way on the right. Now c is representing some specific value of x. If you're doing it in general for a value of x, all those c's would become x's. So let's show, just with definition of the derivative each way, how we could do it. So we'll do the h way first. So we'll have f prime of x is equal to the limit as h approaches 0. And we need f of x plus h. Well, that means everywhere there's an x, replace it with x plus h. So we'll have x plus h cubed. Then we'll have minus f of x, so that's just x cubed, all over h. And really, this is just a slope. It's a change in y over change in x. On the bottom originally is really the x value minus the other x value, but the x's subtract to 0, and you're just left with h. So it's just a change in y over change in x. So x plus h, we'd have to multiply that out 3 times. And eventually get x cubed plus 3x squared h plus 3xh squared plus h cubed. So we've got minus the x cubed all over h. If you did it correctly, everything that doesn't have an h should add to 0. So those add to 0. And divide those all by h. So that would be 3x squared plus 3xh plus h squared. And now we could do direct substitution. So if you put in 0 for all the h's, we just get 3x squared, which is not surprising because you know your power rule from last year. So that's the h way. Let's look at the a way. We would have f prime of x is limit a approaches x, and you have f of a minus f of x. So f of a means replace a for x, minus f of x over a minus x. On top, we would have to do our difference of cubes factoring, which difference of cubes factoring, the first parenthesis is just your first base minus your second base. And then it's your first base squared. And then it's always the opposite sign, so we'll have plus here of your two bases multiplied, then plus your second base being squared. And by base, I mean base of the exponent. Then we have a minus x here, which will divide out. If a was approaching 7, that means everywhere there's an a, we would put a 7. But if a is approaching x squared, or if a is approaching x, everywhere there's an a, we'll put an x. So we get x squared plus x times x plus x squared, which would give us 3x squared. So two different methods, just thinking about it in different ways, but producing the same result. So continuity and differentiability. So f is differentiable at x equals c if the following two conditions are met. So first off, it has to be continuous. If you're discontinuous, you cannot be differentiable. So any jumps, poles, asymptotes, you're automatically not differentiable at that point. So the continuous, you had a three-step check. You had that f of c had to exist. You had that the limit as x approaches c of f of x exists. So within that, the left-hand limit must equal the right-hand limit. And then those two parts had to be equal to each other. So in other words, the y value at the x you're looking at has to equal the limit value. If they're not, and the first two are true, then that's when you have a hole and a point somewhere else. So that's one thing that we need to be true. The other thing is we need our derivative as we approach the value of c on the left to be the same as when we approach on the right. So the meaning of that is you can't have any abrupt changes in the slope. So the slope of the tangent line from the left is the same as coming from the right. A case where that would not be is like an absolute value. Your slope from the left is always a negative number, and it's staying the same constant negative number. From the right, it's the same constant negative number. So therefore, the derivative doesn't exist at the corner point because they're not approaching the same value from both left and right. So the function being continuous at some x value is necessary for it to be differentiable, but not enough on its own. And absolute value is the example of that. Absolute value was continuous at the corner point, but it still was not differentiable. But the first check we have is continuous. So if it's not continuous, it's automatically not differentiable. So on this graph, we need a spot that is continuous and differentiable. And that's true when x is equal to a. At x equals a, it is continuous. You don't have to pick up your pen, and there's no corner point or kink or cusp. Continuous, not differentiable, would be at x equals b, because we've got a cusp or a corner point there. And at c, it's not differentiable because it's not continuous. Just a review of some derivative rules. If you have a constant in front of a function, that is the same as if you pull the constant out and then do the derivative of the function. So if you have 7 times x squared, you could ignore the 7, do x squared's derivative, and then multiply the 7 back in. Our power rule, the exponent comes out front. The new exponent is just one left. Our product rule, we do derivative of one times regular of the other, plus regular times derivative. And order doesn't matter in the product rule because it is a plus. The quotient rule. The first part should have the regular of the denominator and derivative of the numerator minus regular of the numerator and derivative of the denominator all over the denominator squared. Now, when I first teach that to kids, I teach them to remember low d high minus high d low all over low low, where d represents the derivative. So low means the regular bottom times d high, so derivative of the top, minus high, so derivative of the top, times d low, so derivative of the bottom all over low low. Low d high minus high d low all over low low. And our chain rule, you start out, you do the derivative of the outermost function while keeping the inner function the same. And then you multiply afterwards by the derivative of the inside. Sometimes chain rules aren't too bad. Sometimes chain rules can be really challenging. Our trig derivative review. Derivative of sine is just cos. Derivative of cos is negative sine. Derivative of tan is secant squared. Derivative of cotangent is negative cosecant squared. Secant is secant tan. And cosecant is negative cosecant cotangent. And lastly today we're going to do 3 practice derivatives. So this practices 2 things, our rule where there's a constant out front, and also a trig rule, and I guess third thing because it does chain rule as well. So the 5 can just stay out front. Derivative of sine is cos, and we're doing chain rule, so we keep the inside the same, times derivative of the inside, which would be 3x squared. Now, if it's a free response question, you could leave it like that. If it's a multiple choice, it's probably going to be neatened up. They would probably have 15x squared cos x cubed plus 12. Over on the right here, we could do this with quotient rule. We'd have our denominator times derivative of the numerator. So we'd have negative sine 3x times 3 minus the numerator, high, times derivative of the denominator. That's an exponent of 1/2, so we have 1/2 x to the minus 1/2. All over low, low, so square root of x squared is just x. So if it's a free response, you could leave it like that. If it's a multiple choice, if it doesn't match exactly, try and neaten it up. You might have to move the negative exponent underneath, get common denominators to try and get it to match up. That's one of the challenges in this course with multiple choice questions. If your answer doesn't match exactly and you know you're confident in it, sometimes you might have to just manipulate it a bit to get it to work out. When you have trig functions raised to a power, it's helpful to think of it as that trig function all raised to the power. So we have 8 times secant x all to the 4th. So h prime of x, we could bring the 4 out front. We'd have 32. We'd have secant x now to the 3rd. But then we got to do derivative of the inside. So secant's derivative is secant tan. Free response, you could leave it like that, but if it's multiple choice, still have it neatened up. So we have 32 secant to the 4th x tan x. Now that could be neatened up possibly even more, because tan is sine over cos, secant's 1 over cos. You could see it written as 32 sine x over cos to the 5th x, and that would be equivalent. Right. So you have you can be if you have questions from the summer packet still, you can post them on the discussion board or ask them next time you're synchronous. You can be working on tonight's homework. You also have problem set you can work on for Friday, and you can be re-looking through the summer packet to make sure you're ready for the test for next week.